Good morning, everyone. Thank you for your interest in joining this webinar. Today, we are going to discuss the seismic analysis and the required modeling in ETABS for the latest IS1893 2025 code. And today's agenda will be focused on these listed points, basically the brief discussion on the code requirements and the modeling code requirements in ETABS, and all of these in a step-by-step approach in an example to perform all three analysis methods in the program. So it is restricted only to the analysis part. Let us start with the methods of linear structure analysis as per table 9 of part 5. Right. So they are given a precise table where you can reference decide on the method of analysis that we are going to use for the project. But primarily, these are governed by the building height up to 50 meters, and then regularity and the seismic zone. If you take a seismic zone, then all the methods are applicable. And there are restrictions for the equivalent static method, which we will discuss shortly. And based on building category, you have the special and critical sections requiring response history method. And if you take the building configuration, any irregular buildings require the dynamic analysis, either response spectrum or response history analysis. And taking the time period, the approximate natural time period TA calculated using the formula given in the code, then if it is greater than 4, then dynamic analysis are applicable and are recommended as per this table. Now, our agenda is to implement all the three and give you an introduction to these analysis tools available in the ETABS program. Regarding the equivalent static method, so it is applicable to structures where the first translational mode accounts for at least 80% of mass participation. This has to be ensured to use only the equivalent static method. So for this, we'll have to perform a modal analysis and find out the modal mass participation ratio. So this section gives you the approximate fundamental natural period TA that is to be used, calculate the time period, and then the base shear and distribution of base shear in a quadratic form along the height of the structure. Then we have the response spectrum method for irregular mass or stiffness distributions and recommended for structures with TA greater than 0.4 seconds in general. And the recommended modal combination method is CQC. And we have to ensure 90% modal mass participation from the modal analysis case that we are using. And then we have response history method, recommended for critical and special categories, although it is applicable for all categories. So basically it requires ground motions, which are supplied by the BIS. I'm not sure whether it is available in the BIS website at this point of time, but once it is available, you can utilize them, considering 30 ground motions for zone 2, zone 4 for far field earthquake records, and in case of near field earthquakes that you're considering, then you need to consider 60 ground motions. This is recommended by the code. And then the ESM will be the benchmark, that is the minimum base shear. In case the dynamic base shears are lesser than this, then those base shears need to be enhanced for this ESM base shear. This is similar to the previous code, and deformation responses need not be amplified. So these are the important things that we need to consider when you're using the respective type of analysis method. And the model that we have prepared in ETABS that needs to satisfy these, which ETABS is already doing just for summarizing the geometry. So we are modeling the geometry accurately, the configurations and irregularities, either to stiffness or masses, right? So material properties and mass and stiffness are accurately modeled in the ETABS program. The boundary conditions, support conditions must reflect actual site conditions. That means in case of soil flexibility needs to be considered, then the guidance is given in the code itself for soil flexibility. That needs to be adopted. And then the shear deformations, the effect of shear deformations must be explicitly included in the stiffness matrices, which ETABS already does. And then for the analysis, effective section properties to be used is given in table number 3. Clearly for each type of structural member. Compared to the previous code, now we also have the effective shear area to be considered in the analysis. So I have summarized the modifiers specifically for concrete buildings in this table of the slide. So blue colors are area objects, and then red colors are for frame objects. And then the earthquake hazard or the base shear, design base shear that we need to calculate. So all the formulas and the spectrum, all of this we had discussed in the previous webinar itself. For completion's sake, I'm sharing those slides again. We'll be using two different spectra for the equivalent static method and then the response spectrum method. For time history or the response history analysis, we use the ground motions directly. So other inputs such as I, R, and Z are obtained from the code. These are clearly given, and you can easily select them from the code. And last thing that required is the cantilever projections. We are not modeling in this example, but in case it is considered, then these are to be taken care in the design with enhanced forces that is given in the code. Now let us switch to an example. So we have an example model that has special moment resting frame and structural walls, special structural walls. Now we will begin with the equivalent static method. So as you know, the implementation of the code takes some time. So we have provided you a helper. We can make use of that, or you can also directly model these. Let me quickly take you through the basic definitions that we need for all of these three types of methods, starting from the mass source. Just going to get to the seismic weight. We'll modify the existing one, specified load patterns, dead loads, 100%, live loads, 25%, and you can also include vertical masses. Next step is under the load patterns. We need to define a user coefficient based load pattern for the seismic loading. So EQX, EQY, and EQZ. So EQZ, I'm keeping it none. We are not going to use it, but for completion's sake, I'm having this here. So for the equivalent static method, we are going to consider only the lateral excitation. So basically, the user coefficient will have this definition, how we want to consider this direction and eccentricity. I'm considering only the X direction without any eccentricity at this point of time. And for Y, specify this. The rest of the things, basically the base shear coefficient and the exponent K will be calculated using the plugin, or you can also calculate it directly and provide it here. So I'm going to use this plugin now to update these coefficients. Then you can run the analysis with those updated values. So I've added the plugin using this tool and seismic hazard inputs. So the input parameters, this is for zone 3, a normal building category, and structural system, special structural wall, and special moment resisting frame with boundary elements. Site class C, and time period method. We can provide these values. Currently, some manual input is required, 1.2% for the columns and shear wall term in the denominator of the formula. Calculated this, just feeding those values, 0.1446. Masonry walls I'm not considering, so I'm keeping it 0. This is for the X direction. The building height is 15 meters, 5 stories, 5 into 3, 15, and then X dimension is 25, and then Y dimension is 15. So for the X direction, I'm going to calculate this. And see, these values are calculated. In any case, you want to update this with the user value, you can do this before updating the load pattern. So I'm accepting these values for EQX and update, right? And you'll get a message that EQX updated. And for Y direction, I'm going to update 15 meters, recalculate. This time for Y, we'll update this. You can see EQY updated. And for reference, you can save this report for future reference. And then we also save the response spec functions that are required with this parameters involved. Will be ready to use in the response vector method. We'll save this. We'll get where it is saved. I mean the location. And then for the vertical, saving this. That's it. Before running the analysis, we will also apply the effective section properties based on this table. Let's start with the beams. So we'll select all the beams and assign them with property modifiers. Here 0.4, and major direction bending 0.35 as moment of inertia I33. Next, we select the columns. Effective shear area is 0.7, and moment of inertia is 0.7. Basically, all values are 0.7 for the columns. The shear area in both 2 and 3 directions. Process, I will select all the walls. And assign them with shell stiffness modifier. For the walls, effective shear area supposed to be given in the F12 as 0.7. Again, for walls, it is all 0.7, but note the parameter which we are modifying this, F22 and M. This is out of plane bending. F12 is in plane shear. And apply this. All right, we're all set to perform the analysis. So that is one requirement from the code. that we need to check, which is for using only the equivalent static method, we need 80% model mass participation. Let us run this analysis. We quickly update load cases. We'll also have a quick look at the model. Let's say 15 modes with the eigen. But since we are also considering the vertical excitation, I think it is better to use the RITs, which will convert faster with lesser number of modes. So we can go with UX, UY, and UZ load vectors for the RITs model. We can run the analysis once. Right. We will check the model results at this point of time to ensure. Let's start with the model periods and frequencies. First mode is 0.747, second mode is 626 and 0.5, well separated. But we'll check the model participating mass ratios, and you'll see the first mode, the participation ratio is 73%. It's not 80%. In the second mode, it's 72%. The third will be a torsional mode. It's about 71.8%. But as per that requirement for the ESM, 80% is not achieved. So anyway, we'll be forced to use the dynamic analysis, either response spectrum or response history, based on other considerations. Now let me have the response spectrum defined. We unlock this. So we created the response spectrum functions from the plugin. So I'm going to use them as response spectrum functions. Response spectrum function will add this through from file, add new function. We'll browse this. So please note, this will be your text. So we need to make sure this is text, and can find this horizontal function saved. We'll name it as IS1893 for identification. For horizontal one, we'll add the vertical one as well. We'll create the spectrum cases, call it as RSAX small spectrum, and it is acceleration in U1 for X, and the function is horizontal function, and the initial scale factor will be G in millimeter per second square. That's the model unit value for acceleration. And it is based on this model. CQC method is followed. Directional combination. It's default to SRSS, but we are handling these as one component per direction. You can include other components if you want to apply or combine other directional effect. Yeah. And the model damping is 5% of critical damping. And I'm not considering any eccentricity at this. Right. I will create a copy and provide it for Y direction. Same function. Create one more for Z. U3 function should be of the vertical one. Rest are all the same. Right. All right. You're performing the analysis once again. You will check the base reactions. Right. So the EQX is 1057 kilonewton. And from the dynamic analysis, response spectrum method, I think 764. So this scaling has to be done because it is lesser than the static. And no scaling for the vertical direction because it is using a separate spectrum function without the response reduction value. We update this. Scale factors in respective directions. Okay, I'm going to unlock this once again. I will also include the load combinations. We'll add one combination. This will be, call it as CS0. It will be 1.5 times of dead and 1.5 times of live basic gravity combination for the design. And other combinations I'm going to bring in from the plugin. We'll use generate load combinations and get load combinations. Enable spectrum cases. So there are combinations, I mean, the additional combinations specifically for the concrete and steel, which is given with omega factor. So currently, the program has not been updated yet. So we will have to handle this in multiple model approach, one with the combinations with these, I mean, without the omega factor load combinations or the additional combinations, and one with, because omega factor is applicable only for the vertical elements, and then shear walls will have another uh, omega factor depending on the aspect ratios. So these needs a proper implementation. At this point of time, we'll have to handle it in one more model that we'll have to have only this combination and have this. For now, you can also have the additional combinations in the same model just for demonstrating this. So I'm going to use mutually orthogonal planned directions. These I'm going to consider 30% of the other direction of the seismic loading and create the load combinations. And you can see, so this one creates, and it also creates the additional ones. So first set is for the equinostatic method and second set is for the response spectrum. So both will have the set of additional combinations. Right, now let me add this to the model. It's done. We'll close this. You can see all the combinations. So this step, I'm doing this to show another requirement for the P delta analysis. As per the code, it means you'll have to perform the design once. IS456 and rest are all default parameters for the design. Concrete frame design combinations. I'll exclude these combinations. Additionals for now, having only the regular combinations. And then perform the design of these members. So currently the code is suggesting to check for this stability index Q. If it is less than 0.04, then a linear P delta analysis is not required. However, our recommendation is always perform a P delta analysis based on iterative on loads, which we usually do with the P delta options, or converting the design load combinations to nonlinear static that will have the P delta effects, right? So this is only to cover that clause of the code, but what you will get is after the design, when you right click and quickly get into the details, and in the summary, you can see the K factors used, less than 1, it means these a non-sphere category of the frame. You can see the Q factors here can check at critical regions, a particular column member along a column stack, critical stories to identify the queue and proceed forward, which is available only after the design. And it is a part of design 0.01, but you can get it in the summary itself from the K values that it is a non-sway frame and P delta may not be required as per that. But I'm repeating that we recommend performing the P delta analysis always. Okay. So this is to cover that clause of the code. So now you can see the response spectrum method and equivalent static method. Their Bayesians are matching. We can proceed with the design of these members. Now, third analysis that we want to consider is the response history analysis. I think we need the scaled ground motions should be available through the BIS. For demonstration purpose, I'm going to use a raw sample earthquake that is available with the program to demonstrate how it is used in the program to apply as the acceleration loading in a time history analysis. Let me unlock this model and we will go to functions, and there we have the time history. Right? And we'll have to import these functions. Whether it is from the BIS or other source, this is how you have to do this. So it is a general way of accessing those files. From file, add new function, and then you'll browse, and it'll go to the install location of the program, and you'll find a time history function folder, and you'll find a few sets of earthquake data. Each earthquake will have three components, 1 and 2 is for the X and Y directions, and then Z for the vertical. So let me add one by one. Let us use one earthquake. So we actually you will have to use 30. So I'm going to use one for demonstration purpose. So one will have three components, one, Altadena 1, and that will be added. Basically, it has, if you go and view the file, in a text, do not modify this, but note this information about the earthquake. This is Altadena, the name, then recorded station, the degree, 0 degree, and then 2000 points of acceleration data equally spaced at 0.02 seconds, and the unit is centimeter per second square. Right? And each record is saved as 8 points per line. So the program has an inbuilt capability of reading the various formats in which the time history data is provided from various sources. So you can utilize them. I'm going to use all of this information, but since it is a sample, so program has already filled these fields, header lines to skip, number of points per line, 8, and values at equal intervals of 0.02 seconds, right? So, and you can see the record, and it is for 40 seconds approximately, right? And most of the excitation happens for about 10 seconds, and then the decay of the spikes you can see. Right. Now quickly we'll add other two. For the vertical. Next, we can use this the time history functions directly in a time history load case. However, there is a scaling is always required based on the region or the site spectra or the design spectra, which is usually done, which is also available in the program as an additional tool, which I'm going to use because these are unscaled recorded seismograph data. So now we'll have to scale this for the design purposes. So if we use the BIS ground motions, they are scaled for Z values already. So only you need to scale it for the R value depending on the structure. So they have simplified many things if you're using it. And in the load case, you can simply specify the R value as a scale factor and proceed with this. Now, what I'm going to do is I'm going to show you additional option in case you are inputting a raw data like this, then we can do it with the match to response spectrum. Then you add new function. Let's name it function 1 because we are going to use on this 3 sets, right? So naming is not that important, so I'm keeping it for. I'm going to use a target response spectrum, which will be the horizontal one, and response spectrum acceleration units and G units, and then the Altadena 1 time history, and then its acceleration units is centimeters, the input. And then we can match this for this design spectrum in frequency domain or time domain options are available. Or you can use any other third-party applications for the scaling, or you can also do it on your own. Then finally bring those time histories as a simple file input. But I wanted to show the features available in the program readily for your requirements. So match time history, right? Okay, show the match time history, and you can see the design spectrum, and this is the matched one. You see both. You can see the actual one, which is very high, and this is matched for this spectrum with all factors involved. So it is. So I'll do this quickly for the rest of the time histories. Vertical. All right. So this is raw data, and then we have the scaled match to response spectrum data. Now we'll have to define the load cases for the time history case. Let's call it as response history analysis in X. We'll select the case type as time history, and program offers you various subtypes such as linear model, nonlinear model based, or direct integration, whether linear or non-linear. We will use a linear model because our analysis type is going to be linear and it will be model based. So load pattern is acceleration. In U1, function is function 1, the response spectrum matched time history. The scale factor will be 9810, the G value, and it will be based on this model case. The transient type motion and then number of output time steps. This is 100 steps at 0.1 seconds, the default values. I'm going to use this, but you can refine this to much more lesser time period, maybe matching the time uh, delta t value of the input or other variations. But this is about 10 seconds. That should be sufficient. And model damping is 5% for all modes. It's the requirement satisfied for the code. And we'll create a copy of this case for other directions and we'll update this. Sorry, I need to update the direction as well. For Y direction, it is U2. For X direction, it is U1. And Z direction, it is U3. Respective functions. All right. Now we can perform the analysis. Right. So the messages are informational only. It's okay. So warning message is nothing but the time history function value at the start. Okay, so that will be ignored. That is okay. Now we'll have quick check on the base reactions. Right. And you can see the response history cases for X direction and Y direction, and as well as Z direction. Some scaling is required here. I will skip that, but it is the same as what we did for the response spectrum method. So the 9810 initial scale factor needs to be applied with this ratio, and then we can run it again. But I wanted to quickly discuss the outputs from the response history. So we'll get response spectrum curves. This is another output required by the code, or can also call this as the floor spectra for designing the secondary systems mounted on primary systems. So you can see this is at a particular joint. So for RHA in X direction, so if I joint in X direction and acceleration is plotted. Right, for various damping ratios, you can modify these values for which damping ratio you want to see. And you can get this spectra from various levels, and you can export this table to Excel for further use of this data. So this is one important output after the time history or the response history analysis. Next, you'll get the plot functions. Can select any joint, for example, this joint, and then get into the plot functions. And you can define a plot function. The default plot is for the total base shear versus the time. You can add the FX button, can add more functions. And for various outputs, for example, joint displacement, joint acceleration, let's say joint acceleration at the roof level, we'll name it roof acceleration in X direction. So you'll select the joint acceleration, story 5, and you can select a particular joint, and then you can select the response type, absolute acceleration in UX direction. We have this. Right. Once this is done, you can update the vertical function. So horizontal function remains time, roof acceleration. Just for quick comparison, you can add one more, just input load, acceleration in direction 1. Or you can call this as ground motion. And add both of them and see the accelerations in comparison with the ground motion or the input motion with the response. Right, so many things you can do with here, not only for the acceleration, displacement, velocities, member forces, base shears, right? All of this are possible with this plot. But for our requirement towards the design, we can straight away use this analysis results in the design. But that discussion will be in another session, not for today. The program can handle the response history results in the design as well as an envelope or step by step. We go to the, I'll quickly show that, and you can see the multi-response case. It handles it as step by step by default. It, if the code requires you to do an envelope, it can do the envelope also. So you can select from here or step by step. That means design is performed for each step, and then the maximum is picked up. Right. So the design using all three types of analysis methods and their results is possible within the program. So I hope this was helpful to start using any type of analysis method in your model. Let me see some questions. Okay. Yes, there is a question on raft modeling. Yes, we need to model the raft. The guidance is available in the code where you can exclude or include the foundation system with the soil stiffness, basically this flexibility. You'll have to do this. You have to model. I did not do this because it will take more time to cover all of these aspects, but we are planning to cover one more session on that in the future series of this webinar. Please look forward to it. Okay, SPD for the columns and walls. I think this is explained in the code very well. Yes. as a percentage. Yeah. Slab modifiers for this model did not apply because it is a membrane type we are using. In case of shells, the out of plane uh, bending stiffness has to be considered as given in the table. Yeah. So there is a question on the plugin. I think it is available in our website www.csiesvl.com. Please check us and also let us know. We will share it with you. Yeah. Regarding the ground motions, yes, BIS will provide this very soon. You will be able to download this. And these are ready to use. As I said earlier, just need to use the scale factor for the R and use it. So enough discussions are available in the code itself, in part one. Yeah. So yeah, torsional eccentricity, yes, we have covered this earlier also. It still remains the same, but you can look at that webinar, which is available in our YouTube channel. This webinar will also be available in our YouTube channel. I think it is live, and then the recording will also be available after that. Yeah. So in model case, we used RITS instead of the eigen. So eigen is basically uh, trying to capture all the modes possible in a system. So RITS are specific to the load vectors that we specify, which we are interested in. That's the reason we are going with the RITS, and it requires less number of modes to capture the relevant structural modes instead of the eigen. So that is the main reason behind. Yeah, if you need a okay, there is a request to discuss a response history analysis with more details in a different session. Yes, we will, as we get more details on the new code for the ductile things, then we will consider doing this one very soon. The Q factor we were discussing in the column output is the stability index. One of the requirement for the ESM, I mean equivalent static method. So the plugins available for the latest versions only, 23 onwards. Yeah, the overstrength factor for the columns and shear walls, uh, it is a design requirement which needs to be considered in better in two different models so that you will get in contrast result outputs for the regular combinations and the additional, and then you'll have to use the higher one. But it requires a proper implementation in the program, which we're also working on and will be released soon. Yeah, the design eccentricity, it requires 1.8 as a factor now compared to the previous one as 1.5. Uh, so it has the inbuilt 1.5 based on the previous code. So do not use the eccentricity, but use the override values. Manually calculate this eccentricity and provide it. And you can still use it. Yes. Yeah. There will be another session we are planning to consider the podium and the tower, right? So that kind of system needs some more discussions. We are planning one very soon. Yeah. Yeah. I hope I have answered most of these common questions. If anything is specific, then please feel free to write to us for any specific query regarding your model. We're trying to model, have issues in that, and we are open to help you on that as well. So thank you all for joining. We'll meet you in another session very soon. Take care. Bye.